Is he in this one? Where's he?
Hello. Hello. Yep. Can I start? Yeah. So, good morning, everyone. My name is Eduardo. I'm from ITA Rocket Design, team number ID 73, and our study case is the wind tunnel test of our previously year rocket. So, really quickly, we are going to present the motivation of our work. We are going to show you like a flight overview and tell you the wind tunnel characteristics that we tested our rocket, and show you the solution to join the rocket on the load cell of the wind tunnel. And then we are going to show you which transformations we used to choose the wind tunnel conditions, flight conditions, using the Brandon-Glauer transformation. Then we are going to show you on graphs the results and analysis. And finally, we are going to conclude what we learned with these tests. So first of all, to introduce you to the problem, in IRAC edition, our rocket reached an apogee of 7,834 feet. However, we calculated with using our 6 degrees of freedom simulation an apogee of 9,800 feet. And this difference of around 2,000 feet damaged our competition score, and so we had some hypotheses for why this happened. And first of all, we thought that our DETCON flight coefficients were subdimensional, especially the drag coefficient. We thought that our DETCON model wasn't appropriate for our rocket, and we wanted to test this. So, and the other possibility is that you see in our rocket flight video is that our rocket rolled rapidly during flight, and we didn't expect that. And we think that because the fins were misaligned, that the rocket had this roll during the flight, and this could also damage our flight performance. So the solution for this problem is to use like wind tunnel or CFD analysis to check the aerodynamics coefficients. So this is our rocket in the launch pad, ignition and liftoff. So in flight, you can see it roll considerably, and we didn't expect that from our simulation. You see later that DATCOM considered that the fins were perfectly aligned, and because of that, the rocket wouldn't roll. However, you can see in the flight video that it rolled considerably, and we wanted to understand why this happened to come with a solution for the next year's project. So the wind tunnel, it's a mid-sized wind tunnel in the Feng Laboratory in Aeronautics Institute of Technology. It is 40 meters long, and the test section dimensions are 1 meter by 1.28 meters and 4 meters. The turbine that powers the wind tunnel has 200 horsepower, and it's an 8-blade fan. The maximum speed we can reach with this wind tunnel is of 53 meters per second, and with a turbulence level of around 0.05%. The load cell in the test section can measure in 6 degrees of freedom the 3 forces in an orthogonal axis and 3 moments also in these axes. Oh, and this is like a quick overview of the wind tunnel. So these are some pictures. In the center picture, you can see the inlet. It's a large inlet, and the outlet view on the left. And in the right picture is the turbine that powers the wind tunnel. So the first technical challenge we had was to make the integration of the rocket on the load cell. For this, we came up with an 775 low tolerance aluminum part with slots and threaded holes to adapt these. So in the center picture is the female part we designed, and it has a slot that matches the male part that is shown on top of the left picture. And there, with precision fastener screws, we fasten them together. And finally, when we take part of our rocket fuselage that is in the right picture, and we fasten it in the part in the center picture with M6 screws. So the rocket is securely attached to the load cell, and we can acquire data without much vibration and other mechanical interference. So the first picture on the left is the rocket joint in the load cell, and the right picture shows how the fins were aligned in relation to the rocket axis. We can see that the center fin had an angular offset of around 22.5 degrees from the center line, and that's how we attached our rocket on the load cell. So the test speeds. We began with 4 meters per second, then 16 meters per second, then 35, and then 44 meters per second. We also tried the limit of the wind tunnel of 53 meters per second. However, at this condition, the rocket vibrated a little. So we chose, for safety reasons, to not use the 53 meters per second speed. So for the analysis and results, we chose the 44 meters per second test because the results were much better in terms of uncertainty. It means that for 44 meters per second, we had the least mean square error of the data. So we chose this to make our analysis and discarded the other speeds. And to simulate the entire flight from liftoff to apogee, we simulated for pitch angles from 0 to 10 degrees and yaw angles from 0 to 10 degrees, one at a time. It's important to say that the load cell makes it's controlled remotely, so we set it like a path of tests. And the machine did it all automatically. We would close the wind tunnel and play the test, and it would change the degrees and acquire the data and save it. So the results. To sum up the wind tunnel conditions, we reached a Reynolds number of around 440,000 and a Mach number of 0.13. On the top right figure, in blue, is the aft force, and in this case is the drag force of our rocket. And the red line is the normal force, and the yellow line is the side force that we acquired for pitch angles. In the left picture, it's a similar data, however, for yaw angles of attack. And for moments in the three orthogonal axes around the center of gravity, the black curve is the pitch moment, the blue curve is the yaw moment, and the yellow curve is the roll moment. And again, the first picture on the right is for pitch angles of attack, and the left picture on the bottom is for yaw angles of attack. Even though we made all of the simulations for several angles of attack, we wanted to analyze especially our cruise flight conditions. It means that our angles of attack were near 0. We wanted to check the drag coefficient and roll coefficient during the cruise flight condition. So for this, we simulated in Mach around 0.128 with 0 degrees of with 0 angles of attack, both yaw and pitch. We calculated the forces and moments for this condition. So, like the raw data that we obtained, we fitted these 5 points for each force, and we came up with the average coefficients of our rockets, aerodynamic coefficients of our rocket. So for the analysis, we have proposed for drag and roll moment, we had a drag coefficient of around 0.387 and a roll moment coefficient of around 0.360. However, this was made for a Mach number of 0.13, and our rocket reached a Mach number of around 0.8 in cruise flight condition. So we had to make a Prandtl-Glauert transformation that we found in literature, and the beta parameter is the correction for the Mach number. So we applied this connection using the formula below, the beta parameter. That is, the new coefficient is our wind tunnel coefficient divided by the beta parameter. So we obtain with this transformation for a Mach number of 0.8, you can see on the left table, drag coefficient of around 0.645 and a roll moment coefficient of about 0.601 with this transformation. And in the right table, it is our DATCOM missile estimated coefficient. You can see that for drag, it was below our estimated coefficient using the wind tunnel, and because of that DATCOM considers that the fins are perfectly aligned, the roll moment coefficient is equal to 0 to any Mach number condition. So this graph concludes our work. It sums up actually our work. So the red line is our 6 degree of freedom dynamic simulation using as input the DATCOM flight coefficients. The yellow line is the same simulation, same computational simulation, however, using our wind tunnel coefficients as input for the simulation. And the blue curve is our flight curve that we obtain using the sensor stratologger from the previous flight on the 2017 Iraq edition from our rocket. We can see that the apogee match much better using the wind tunnel coefficients than with our computational estimation using DATCOMs. So the conclusions. We clearly see that the DATCOM's drag coefficient is subdimensional, and it didn't account for rho. Also, we can see that changing the input parameters for our simulation, we obtain apogee of the variation apogee changing the input from DATCOM coefficients to wind tunnel coefficient was of minus 2,000 feet, and it matched almost perfectly with our flight data. Also, making the relative errors, we had an apogee error of around 2.5% using the wind tunnel coefficient, and relative error using that one coefficient is of about 25%. That is like a 10 times better estimative for our flight apogee. So we also learned that even little things, deflections, causes an increased rho amount in our rocket. So for the next year, we are learning and planning a way to align better the things so we can control better our flight. Also, knowing our rho moment, we can learn a way to control our rho, the role of our rocket using either movable fins or gas thrusters in order to control the role of our rocket and make it fly straight. And also for future work, we plan to develop a CFD model to compare the computational data with the wind tunnel data and make a closed loop in our aerodynamic design of the rocket. Finally, I'd like to thank Ezra for giving us this opportunity of sharing our work with you. Also thank the technicians in the FENG laboratory in Brazil and Professor Klein for his guidance in this work. And thank our sponsor Fiesp and New Technique for the support. And thank you guys for the attention. Now I open for questions. We didn't have time to use these results in the rocket this year because it began in the beginning of this year, this work. But we are planning to do this for next years. Well, this year, because of this, we now know the drag coefficient. We bought a bigger motor. We designed a bigger motor. So we basically we used this data for this year's competition. Yeah. Yes. The external geometry doesn't change. However, our internal components change. We began doing some meshing in our rocket, and we analyzed the transition and the nose cone, and we didn't find a Mach over 1 using CFD. Only Mach like 0.96 or something. So we believe that we don't go supersonic. However, it may happen. We expect it don't happen. Yeah, but we believe it doesn't happen.
Yeah, question. How far, were you able to measure how much misalignment you had in your fins?
Not yet. We didn't. Yes.
Just a question on .com. Do you have a graphic user interface board, or do you use the old-fashioned text style?
We still use the old-fashioned technique style. Yeah. We design a MATLAB code. It's a 6 degree of freedom that uses input of moments of inertia and thrust curve, and everything changes in time. So it's a dynamic simulation, and we can predict like how our flight is going to happen. No, we didn't. These works of flight simulations are articles that some of the students in our university made, and I believe they validated somehow during the development of the code. But for the competition, we didn't compare ourselves the results. We designed a better way to attach our fins with we made a base where we would place our rocket and then attach our fins, but it's not a perfect design. So we believe we still are going to experience roll this year, but we expect it's going to be less than last year. So, no more questions. I invite everyone to go check our exhibit poster in the other room. It's team number 73. And thank you very much.
There's no substitute for more thrust. But don't worry, get a bigger motor. Yeah, right.
So, hello, my name is Ari Rubenstein, and we're going to be covering the development of a student research and design flight computer. We're both students at the University of Buffalo, part of the SEDGE chapter there. And we wanted to build a cheap flight computer we can use that met three main requirements. We wanted to track and record flight telemetry, we wanted to deploy a recovery system, and we wanted to have reliable GPS tracking. Now, we had a fourth desired option requirement, which was to record video, which while not part of our three main options, we wanted to do because it's a very cool part of